So my name's Stephen Furmanek. For those of you who attended the clinical research course, you may recognize me. I've also given some presentations on some of the more biostatistical topics that we've had. And so this is actually kind of a follow-up from our clinical research course, in that we talked a little bit about propensity scores, especially I think during the Q&A at the end. And I've had a few more questions about it since then, so I figured this would be a good idea to follow up and kind of talk about them. So I'm a biostatistician here within the Norton Infectious Diseases Institute, and as well, I am one of the people that are kind of putting together the team for our clinical research support program. So if you are interested in that, you'll end up contacting me. So and we can put my contact information in the chat as well for anyone who's interested in that. But as we said, going back to the topic of propensity scores, we have to kind of start with why we would use propensity scores, and that is ultimately going to be so if you recall from the clinical research course, and we have it here as just a refresher, a confounder is a variable that impacts both the predictor and the outcome. So a lot of times what that means is that it's associated with both, so it muddies up whatever true relationship exists between our predictor and outcome. And in any sort of health sciences or medical or sciences, we know that the health outcomes are going to be the result of many factors. And so if you remember a PICO study question, which is, a population, intervention, control, and outcome, all of those study questions will have to manage confounding in some way. And usually we do that by study design or through statistical analysis. And so confounding is an important thing to do. If you don't account for it, then ultimately you don't have very good grounds to say that the relationship you saw, you don't have good grounds to say that that was actually due to your intervention or your risk factor, or whatever your main predictor is. If you don't control for confounding, then you essentially don't have a study to some extent. And so then our options for dealing with confounding, there's three major ones, which are randomization, matching, and adjusting during analysis. So randomization and matching are both what we would do during sort of the study design and planning phase. And then just adjusting an analysis would be something that happens kind of after the study is performed and we're doing analysis. And sometimes you can end up doing multiple options of these. You may end up randomizing, but still adjusting an analysis. So let's kind of take a deeper dive then into what randomization, like the pros and cons of it. So for randomization, it allows you to account for any number of confounding variables, either known or unknown. So if you randomly assign people to a group or an intervention, then there is nothing that is the process by which they were assigned to that group is totally independent of any other factor. And so randomization is useful because it allows us to use simple and powerful statistical tests, powerful in the sense of statistical power, that they are the most able to detect an association or a difference. The cons of randomization are that it's for prospective studies only. It may not be feasible. In the case of like a surgery, you can't have a placebo control there because you're performing surgery on a patient. It may not be ethical to do so. And it could also be very time consuming if you have certain randomization schemes may require more work. So unfortunately, while randomization is often touted as like the gold standard for adjusting for confounding, the reality is that it's not usable for most study designs, especially because observational studies tend to be what most studies in medical literature are, just because that's where you really generate new ideas. Whereas the randomized controlled trials, those are a lot more specific and a lot more targeted. So then if we look at observational studies, we could look at matching. And so in a matching, what you would do is you would say, we know that, say, someone's age is a confounding factor. So we might match patients based on their age. And so when you use matching, you essentially are ensuring that the risk factors that you have are evenly distributed among your sort of treatment and control, or your at-risk group with your not at-risk group. And then another advantage of matching is that if you have like a large sort of secondary analysis of a database or something of that sort, you can increase your statistical power by increasing the number of matches. So you could have like 2-to-1 like controls to cases, or you could have 4 controls for every case. And then matching is also has disadvantages in that we can only match for known confounders. So randomization, the adjusting for unknown confounders is a big advantage there. And so that's going to be a limitation of almost every non-randomized study design, is that unknown confounders could still potentially exhibit some influence on your results. Another con is that it's time consuming. It'll require special statistical methods. So usually there's special tests that account for how your patients are matched. And then if you have more matching criteria, you're less likely to find matches. So if you want to match on, say, 5 things, then it becomes harder and harder the more criteria you add to match. And then finally, we could also look at adjustment. So typically what this means is that you just do a multivariable regression. So depending on your outcome type, that could be logistic regression if it's a single like a binary outcome of yes, no, like did they experience the outcome or not. If the outcome is something continuous, you could use a multivariable linear regression, or you could use a multivariable proportional hazards regression for time to event data. So there's lots of ways you can adjust for confounders, statistically speaking, in regression models. And there's benefits for doing that. The first is that you can describe the impact of confounding variables on the measure of association itself. So if your main predictor is going to be a certain drug, and you know that there is a confounder, you can look to see how strong of an effect it has based on kind of the level of association that's not adjusted and then adjusted. So oftentimes what we see is that a drug unadjusted looks like it's very, very effective. And then when we adjust for confounding variables, it looks like it may still be effective, but it's generally going to be not as effective in terms of the magnitude of effect. And so then confounding variables, especially if they're risk factors, could also be used as secondary objectives. So let's say that we not only want to look at a drug of choice, but we could also look at, like demographics or medical history or things of that nature. Once again, we're only looking at known confounders this way, though. And usually doing this will require a large sample size. And so the reason I say that is, we'll dive into that a little bit more, but the more variables that you adjust for, the more essentially patients you'll need in the study. So this works well if you have a large cohort of patients, but for a lot of, more typical research, like say that you have a fellow doing a research project or a resident doing a research project, you usually won't have a large sample size that allows them to do this as easily, because they're going to be collecting all this data themselves. And so if you have a smaller sample size, then you run into the idea that you are over-specifying your model potentially. And then there's always the possibility that if one of your confounders is very strongly correlated with your predictor, then you could run into issues of multicollinearity, which essentially would violate assumptions for the model. So going back to sample size, one of the rules of thumb that we have, especially for logistic regression, so if we are looking at binary yes, no, did the outcome happen or not, in general, we can afford one confounding variable per 10 outcomes experienced in the smallest comparison group. So what that I'll have an example here in a second to kind of show what I mean by that. But let's say that we only have 10 outcomes in our at-risk group, then we can really only afford for a one confounding variable. And so you can kind of think of it visually. Let's say that we have let's pretend that our data exists in this scatter plot. So if we have one, like a risk factor, let's say history of COPD. So if we cut then our data into two sections based on history of COPD, so then we have essentially two groups that are being analyzed. Now, let's say we decide to add a patient's history of renal disease. So if we have renal disease and COPD, now suddenly we have four groups. So we've essentially kind of almost split our patient population into 1/4 of what it is for each of these categories. Now, let's say that we decide, and this is only looking at 6 groups, right? So if we have 6 groups, you may notice that there are some groups here that don't have any patients in them whatsoever. So what that does is it will cause issues, and that oftentimes it will inflate your standard error and then make it less likely for certain groups to be statistically significant. Or if you have like a confidence interval that you're doing, you'll end up with this ginormous confidence interval that could be, totally outside the realm of reality. So it's very important to think about how many variables you could actually use. And so some of that comes down to your sample size calculations, but also how you want to sort of approach your analysis. So you could end up in a conundrum, though, where let's say that you have a small group of patients, or a relatively small group of patients, and then you have a relatively infrequent outcome in that small group of patients, but you know that there are potentially a lot of confounding factors. Then the idea behind propensity scores was answering the question, what if we could reduce all of our complexity to just one number? So that's kind of the idea, is that we want to take all of these variables and reduce it down to just one single number. So propensity scores, just a little bit of history. They were introduced by Rosenbaum and Rubin in 1983. There's the citation for their paper. And so a propensity score that they defined is the conditional probability that a participant would be assigned to a treatment given a set of covariates. So in this case, you can think of it like the predicted probability that you would get something as well. And so the reason that they introduced this was because obviously in a non-random treatment assignment, say a cohort study, that you want to be able to show that there is like the effect of the treatment on the outcome. Like you want to be able to describe that without bias. And so they wanted to essentially reduce the bias of non-random treatment assignment. So in layman's terms, and this is still maybe a little bit high level, but what you're going to do to create a propensity score is you're going to create a logistic regression model. So I'm not going to put in any formulas here because I don't expect you all to try and do this on your own. The purpose of this is just try and describe a little bit how we are getting a propensity score. So then your main predictor is going to become the outcome of this model. So instead of having the outcome be the outcome, what we're doing is we're predicting what the likelihood of someone's treatment versus non-treatment, or exposure versus non-exposure. And then your confounding variables are going to become the predictors. So you're going to use these other confounding variables then to predict the likelihood of someone's treatment or risk factor. And so those predicted probabilities then are the conditional probability of receiving. They use the word treatment a lot in that article, but it can be applied in other ways. So that's why I said main predictor here. So let me give you an example that kind of highlights why we chose to use propensity scores for one of our analyses. So in the beginning of the pandemic, what we, Dr. Ramirez and us as a group did was we collected information on 632 COVID-19 pneumonia hospitalizations at 8 hospitals in Louisville. And so we have 632 patients, so that's our cohort size. And so we were interested in seeing if COPD would make outcomes worse in these patients. And so here we have 96 patients that had a history of COPD and 536 patients that didn't. So already we can see that we have, almost a 1-to-5 ratio of patients, of cases to controls, so to speak, or those at risk to not at risk. And then we had 27 patients in the COPD group that died during hospitalization. So if we're using in-hospital mortality as our main sort of outcome, which is what we did in that study, then we can afford essentially at most 3 confounding variables, and that's rounding up for the 10-to-1 rule of thumb, because our smallest group had 96 patients and we had about 30 events in that smallest group. So because there's lots of different things that could account for this, I mean, COPD is a past medical history. There's lots of variables that are correlated with it. What we decided to do was then create a propensity score to predict that. So we used a ton of variables to make this propensity score. And so we used age, sex, race, nursing home residence, lots of past medical history, and social history as well. And so ultimately what that became was, if you look here, we have our sort of predicted probabilities then of being COPD positive. So if you see it goes from 0 to 1, so your probability, is, think of like a percentage divided by 100. So here the probability, like in the middle for these patients, would be they had a 50% roughly probability of being a COPD patient. So in this case, you can see that there is a difference in balance, in that the non-COPD patients largely had a much smaller chance of being COPD positive if you look at their predicted probabilities. So then using these sort of propensity scores that were added, we can then look at a couple of different applications. So if you remember, we talked about adjustment and analysis and matching. So you can actually use propensity scores to supplement those processes. So for matching, instead of matching based on a risk factor, say like, age or sex or race, we're instead going to match based on their propensity score. So you're typically saying that someone who is close in propensity score is a good match. If we go back to our propensity scores, these patients here, if this probably single patient that had this propensity score of 0.6, right? They are going to be similar in patient characteristics to this patient here who had COPD. And that's largely because the way the logistic regression functions, you are essentially creating a predicted probability that's all of those other variables added up together to produce that probability. And so if we look here, you can kind of see our propensity scores. This is actually for a different study. This is looking at our RSV patients for season 1 in terms of matching RSV patients to non-RSV patients. But if you see here, we have, matched treated, it says units, but those are patients. And then we have matched controlled patients. And so you can see based on where the propensity scores kind of line up, this is called a jitter plot, where normally this would just be a one-dimensional thing, but they kind of space it out to make it look more three-dimensional and easier to see. So you can see that for the most part, it looks like patients are relatively well matched in this group. And so there are many algorithms by which you can match. So nearest neighbor matching is the most frequent. There's what's called optimal matching, where you're trying to minimize the differences in propensity score for each pair. And then there's exact matching, which is the equivalent of matching based on risk factor. And so because of the way that you get predicted probabilities, exact matching is typically unlikely if you have any continuous variables whatsoever in your model. just because you would need to have a exact continuous variable match. So generally speaking, exact matching isn't as feasible. So it's not used as frequently with propensity scores. But let's consider then the nearest neighbor matching. So what the nearest neighbor matching does, and I want to kind of illustrate this through a visualization. Let's pretend that on this two-dimensional canvas, these dots represent our propensity scores. So originally they were our data, if you remember just a couple slides ago. So now they're going to represent our propensity scores. So the way the nearest neighbor algorithm works is you're going to randomly pick a starting point, and then you're going to find the closest match to that. So the closest neighbor to this is that match there. So then you're going to move on. You're going to randomly pick another neighbor or another new start point. So let's say we now start from this one down here. The closest propensity score from that one is over here. And so then what we're going to do is we're going to continue matching based on proximity. So you might see something like this going through the algorithm. And then eventually we come to this situation where we may not have an equal number of patients left, right? Let's say, so let's say that we start with this patient, right? So this patient, the closest one that's not already matched. So I didn't mention that earlier, but nearest neighbor matching is called a greedy algorithm, because once a patient is matched, it's no longer eligible for being matched again. So that's why you have some cases where there are patients that have potentially closer propensity scores like these two or these two that aren't matched together. So for this patient, the closest potential match, let's pretend that these are both, controls that we could match with. The closest one would be there. So it would be potentially a pretty bad match. This is all relative, but so you can end up with bad matches through the nearest neighbor algorithm. So typically they're not super common, but it can happen, especially if you have something with like a very high predicted probability of being treated, and there is a less high prediction in the control group. So then when you're matching with propensity scores, the overall balance between the groups are going to improve. So if we were to look at like a patient characteristics table, say before matching and after matching, usually you'll see that the proportion of patients that have certain risk factors, whatever you decided to match upon, those will improve. And what you can use is you can use a caliper. In the example of this one, this patient here that has the really long sort of match distance, you can use a caliper to say, okay, well, let's say that this distance right here, halfway to it, is the max distance that you can do. So that'll throw out that match. And essentially that patient won't get matched. So you can use that to eliminate bad matches. And then because it is a matched data set, you will have to use special techniques for analysis. So you'd have to use conditional logistic regression, typically, if you're looking at a binary outcome, or you could use like a stratified proportional hazards regression if you're looking at time to event data. So you have to use some special techniques to account for the fact that it's matched data. So what we ended up returning to that COPD and SARS-CoV-2 study, what we ended up using was called inverse propensity score weighting. So what that means is that for our treatment group, we're going to weight the propensity score those that are low propensity scores are going to receive more weight. And that's because it's inverse propensity score weights. So if you think about it mathematically, if someone has a 90% predicted probability, you take 1 divided by 0.9, you're going to get about 1.1. But if someone has a 10% predicted probability, if you take 1 divided by 0.1, you're going to get 10. So in that sense, the weight that's given to someone who has a low propensity score is going to be inversely proportional to that propensity score. So we want to essentially highlight the control or the treated patients that have a lower probability of being treated. And then for the control group, you actually do the opposite. You're going to weight the high propensity score patients. So the patients who have the high predicted probability of being treatment but didn't receive it, those are going to have a higher weight. So you have more representation that way. And so what weighting does is weighting integrates into most statistical tests pretty easily. But the big advantage of weighting is that it allows you to use your full cohort of patients. So when we were matching, if we were to match patients with each other, the issue that we would run into is that unless we did 2-to-1 or 3-to-1 matching, we may end up with, as many patients. Like we had 96 COPD patients. If we did matching, we would end up with, 192 total patients in our cohort, because we'd have 96 matched COPD patients and 96 matched non-COPD patients. So you can use the full cohort if you use weighted inverse propensity score weights or other. There's many different ways you could use weighting as well. So just to kind of visually show what I mean, if we return to our sort of propensity scores that we had, if we look at those who were COPD positive, we're going to give more weight to the folks with less propensity score and less weight to the folks with higher propensity score. So these patients down here with lower predicted probabilities, they're going to be more impactful in the model that we do. And then for that didn't have COPD, we give less weight to these patients down here, and then more weight to the patients that are going to be in the higher end, because we're using the essentially we're taking the inverse probability of 1 minus the propensity score for those patients. And so an example of what some of the analysis looks like for that. So for this, here we have a adjusted inverse propensity weight adjusted Kaplan-Meier curve. So we have COPD and is the black line, the red line is non-COPD. And so this is the number of patients that were still hospitalized. So here we're looking at essentially length of stay. So if we look, it looks like patients, the median time to hospital discharge for COPD positive patients was about 15 days. For COPD negative patients, it was about 8 days. So there's almost a week difference in length of stay for that initial first sort of wave of patients that we had. If they had COPD, they were just going to be in the hospital with SARS-CoV-2 pneumonia for a longer period of time. Now, if you notice, this actually isn't a statistically significant difference, but you could argue that clinically, it seems very relevant that there would be such a huge difference. So unfortunately, even with the inverse propensity score weights, we still don't have enough statistical power to kind of show a significant difference here, but it allows us to kind of have a better idea than if we were to do it totally unadjusted. And then here we did some logistic regression models for other outcomes. And so we used the inverse propensity score weighted, this IPWOR is the odds ratio that's essentially resulting from an inverse propensity weighted model. And so if you look in here, we actually, for this analysis, we adjusted for the PSI risk class, which was not something we adjusted for in the original propensity score weighting. And I don't remember what else we adjusted for. If you all are interested in finding out, I can send you more details on this. But if we look, patients with COPD had about 1.75 times the odds of ICU admission, and they also had about 1.5 times the odds of dying in hospital. So they were more at risk for some outcomes. And this is accounting for all that past medical history, demographics, social history in the analysis, and also sort of that severity of disease upon admission. Then the one last way, and I don't have much to show for this, especially because I think we are pushing time, when we adjust, what you can do is you can add the propensity score as its own independent predictor. So if you have a multivariable regression, you may have your main predictor and then just the propensity score as its own predictor as well. So that way you can use the propensity score as kind of almost like a variable, like information reduction process there. So that way, instead of looking at the 20 variables that we adjusted for in that COPD analysis, had we used the propensity score as an independent predictor, we could have also accounted for it that way. So that's kind of a summary of the different ways you could use propensity scores for either both study design in terms of like matching or adjusting an analysis. And so for the strengths of propensity scores, it allows us to control for confounding in situations where we can't due to sample size. So if you remember, in the COPD and SARS-CoV-2 model, we had unfortunately a relatively small sample size for what we would want to try and adjust for. And then if you meet the assumptions of like all the assumptions of propensity scores, they'll have lower variance for a matched data set. They'll have lower variance than simply adjusting for confounders. So that actually is helpful, especially because, your variance is kind of what determines your standard error. And then that also determines, to some extent, your statistical significance, because the lower your standard error, the more likely you are potentially to have statistical significance. So it could allow you to then potentially better detect a difference or an association. And another, there's many ways to incorporate and apply propensity scores in analysis. Now, propensity scores do have some limitations. The largest one is still, because it's not randomized, you can, there's been a couple sort of studies that have a little bit of like sensationalist titles where they say like, mimicking randomization for a observational study. I mean, it's yes and no. Like that's a great overstatement. In terms of unmeasured confounding variables, really only randomization is a way to control for those. So it still has the limitation that there could be things that are just outside your control, that you either don't know about or did not consider, that are confounding your study results. And then propensity scores can't fix biased study design. So for example, let's say that you wanted to look at like a time to event like in your, like a time to event intervention. So if you don't account for the time to when that intervention started, so like let's say we want to look at for like the pharmacy side of things, the time to antibiotics. So if we look at time to antibiotic for, let's say we're looking at like vancomycin versus another, less broad spectrum antibiotic for a specific pathogen. This would be a good use for potentially propensity scores, just because that's such a narrow window of patients that it may be appropriate there. Just because you may not see that many patients with a specific pathogen that are being treated on those regimens. But if the time to antibiotic administration matters and it's not accounted for at all, then that could potentially bias your results. Like let's say that you find out that that organism is resistant to the drug that they're receiving, so they switch to vancomycin a couple days later. That could also be another way that it's biased. So bias not in a bad sense, but bias in the sense that like there are structural issues that may need to be accounted for. And then one last limitation of propensity scores is that the propensity scores have an assumption that there is a strongly ignorable treatment assignment. So in this case, there's what's called confounding by indication, where if you think about it, it makes a lot of sense. a patient who presents as more severe is going to get an escalated level of treatment, right? So in that sense, if the severity like is not like a patient isn't as likely based on their initial presentation to get a specific treatment. Like if we want to look at the invasive mechanical ventilation in terms of how well it is improving patients for pneumonia, you may see that invasive mechanical ventilation looks like it's actually causing harm to patients, because the patients who don't receive it usually have less severe pneumonia and will have better outcomes. So that's what confounding by indication means. So in this case, propensity score adjustment is probably not a good technique to use, because it's not a quote unquote strongly ignorable treatment assignment. So you would have to look at potentially different sort of study design for that. And so then the take home for this is that propensity scores are a good tool for when you have a sample and lots of confounding variables. And there's other tools as well. So there are many different types of tools for controlling for confounding, but they offer a pretty compelling case for when you have either a small sample or you want to try and do some level of like data reduction to not have to account for as many things. And if you're interested in this, or you are kind of experiencing this like from a investigator-initiated study, or you're just interested in doing a study and you've already ran into this issue, I strongly suggest you contact a statistician, because there is a little bit of mathematical machinery going on behind the scenes that is kind of working to cause whatever is going on. So for propensity scores, like you can do them yourselves, but I would just say collaborate with a statistician, and then they could, they have much more expertise in that matter and could help. And on that topic, as we mentioned sort of at the beginning of this, we are looking at trying to, get the clinical research support program here at the Norton Infectious Diseases Institute. We have been sort of building the team and are looking to roll out that pretty soon. So if you have a research project, or you are interested in that, or you have just general need of statistical support, feel free to contact me, and that way we can, I can't make a whole lot of guarantees, but at the very least we can talk about it and do consultations. So right now we don't have any specific hours for that, but it's kind of on an as-need basis. So I will now, I know I kind of went a little over, so I apologize for that, open to any questions that you guys have.
Thank you, Stephen. I do have a question I know this topic is relatively new for a lot of infection preventionists. What are some recommendations that you have as far as reading activities or learning activities? I know you did say contacting a statistician and possibly you, but before, how could they do some homework and some groundwork before meeting with a statistician?
Well, what I would suggest is if you have an area of interest, like let's say you want to look at like your pharmacy and you want to look at specific drug interactions, I would not recommend starting with that Rosenbaum-Rubin article. I wouldn't recommend starting there, because that's very like math centric. So if you are to the uninitiated, that will probably look like a lot of Greek letters and be very scary. So I suggest that there's a couple different like articles and resources that are kind of spell out propensity scores in a little bit more detail, but also for more general practitioners as well. Which what I would suggest is if propensity scores are something you're interested in, just like search on PubMed for like a propensity score adjusted analysis in some way. Usually it's mentioned in the title. It might not be, but a lot of times it will be. So if you have a topic of interest, you could then see how other researchers have sort of presented that, and what they've done with propensity scores for those. Propensity scores actually have quite a lot of use in more of the social sciences and psychology. So it's very commonly used there. In medical, just because of the non-random treatment assignments, is as I said, the strongly ignorable treatment assignment assumption sometimes is a barrier to using propensity scores to their strongest in medical sciences, just because, as I said earlier, the examples I made. So those would be my suggestions. Would be if you're interested in finding out more, I would consult just the medical literature that exists, and look in those. And I can look up a couple of different citations and send those out. If you're interested in learning more, I would say just feel free to contact me, and I can kind of go, if you have questions specifically that way, or want to find out more, I can try to point you in the direction of some stuff.
All right. Thank you, Stephen. I did not see any other questions in the chat. Just as a reminder, grand rounds are recorded and available on our YouTube channel. Next week, Wednesday, we will be back. Dr. Elena Swingler is going to be discussing IV to PO antibiotic administration. So join us again next week, 12 o'clock. If there's any other questions, David, do you have anything else to add?
I do not.
Okay, well, thank you all so much for joining us, and we'll see you all next week.
All righty. Thank you, everyone.
Thank you, Stephen.